Okay, well, welcome everyone. It's 2 o'clock and welcome to this workshop on working with GIS data. I'm Janet Reyes, the Geospatial Information Librarian at UC Riverside, and happy to have you join us here for an hour or so to talk about GIS data, which is a particular kind of animal, right? It's a little bit different from other data that you might work with. And so welcome, and I appreciate your interest in this topic. I am hoping to be able to end the presentation maybe at 10 to 3 or 10 till the hour to allow some time for questions and also for you to move on to your next class or your next workshop. I know there's another one right after this one, so I'll try to do that. I'll do the best I can with moving it along. As I mentioned just a little while ago, for those of you just joining, this workshop is being recorded, and a recording of it will be available at the UCR Library YouTube channel in a couple of weeks, probably. And I'll also be sharing out the slides with you afterwards, so you'll have access to some of this material again. I need to share with you what my background is. I am not a data scientist, so sorry about that, data science people, but I am someone who has used GIS data in the course of my career. Before I was a librarian, I was working with GIS data as a mapper and also sometimes trying to find data out there to help me with my mapping. So I've been a producer of data and also a consumer of data, and I hope that perspective will help you. Especially, I tried to gear this toward, you know, things that are easy to make mistakes on, or like, oops, I wish I knew that. So I'm coming at it from that lens rather than from a strict data science kind of lens. My background was mostly with ArcGIS, but I do know some things, little things about some of the other tools out there, including QGIS. So this presentation does not get specific as far as one platform versus another for the most part. So just so you're aware of that. Anything else I needed to share? I don't have a lot of depth in some of the things I'm going to be presenting. But I am presenting them to you just so they're on your radar screen, as it were. So just be aware of that as well. Okay, so moving on. Before we get too far in, I just wanted to share with you the UCR land acknowledgement. We at UCR would like to respectfully acknowledge our responsibility to the original and current caretakers of this land, water, and air, the Cahuilla, Tongva, Luciano, and Serrano peoples, and all of their ancestors and descendants, past, present, and future. Today, this meeting place is home to many Indigenous peoples from all over the world, including UCR faculty, students, and staff. And we are grateful to have the opportunity to live and work on these homelands. And I will add, when we can, right? We miss our campus, and we hope to be back there all together someday soon. But in the meantime, we do need to acknowledge the people who came before us and realize that we're talking about the way land is used today and how our perceptions of it as we collect GIS data. And that's one way of looking at the land, but of course there are many others as well. There have been over time, there probably will be in the future. So yeah. This is what we'll cover today. Just a real brief overview of GIS. That we'll talk about spatial and tabular data, which are the two basic types of data that's in a GIS. We'll talk about data sources, meaning where you might turn to go find GIS data. We'll talk about some file formats that are common, some of the properties of the data that you'll encounter, and then discussions of data quality, both, again, data that you might generate and also data that you might be consuming, things to look out for. And we'll end with a few slides about data management. And again, I hope by 10 to the hour, we'll have a little time for questions. So to make sure I can cover all this information, I am going to probably just motor through, so you can type your questions in the chat at any time, but I'd like to save those for the end as much as possible if we can, just to make sure I can cover everything. So let's look at a GIS overview real quick for those of you who might not be super familiar with what's going on here. The definition of GIS. Well, there's lots of definitions out there, and I happen to like this one from Wikipedia of all places. It's a Geographic Information System, or GIS, is a system designed to do all of those things that you see in bold font with spatial or geographic data. So you can see right away how complicated a GIS is. There's lots of moving pieces. There's lots of things to think about. You may have heard that there's a pretty steep learning curve for it, and that is true. But it's also a very rich field, and it's one that you can get into multiple different ways with multiple types of data. So yeah, but as you can see, this is a pretty complex thing we're dealing with here. So that's a geographic information system. Let's talk about what is geographic information. So in our context here, it can be associated with place names, such as political units, anything from a city up to a nation, also natural features like rivers or water bodies, mountains, that kind of thing. Administrative units also count, even though they're kind of specialized. A lot of us don't think too much about administrative units in our daily life, but if you're looking at data that's collected by school district, then all of a sudden that becomes pretty important. Same with census tracts or service areas for a company, that kind of thing. All of those things can be mapped. Those are geographic information. Street addresses. This is a made-up street address, by the way, so don't go trying to find this on a map anywhere. But yes, GIS these days, you can load up a table that has street addresses in it, and it will generate a map that has points that correspond to those addresses. So that's another way geographic information can be represented in a GIS. And lastly, we have coordinates, things like latitude, longitude. And then for maps that have been changed from the spherical to the flat, we have things like UTM coordinates, and out here in the Western United States, we have township, range, and section. And there's a lot of other coordinate systems. We will talk about those a little bit later on. Okay, let's talk now about the types of data in a GIS, which the two basic categories are spatial and tabular. And then within spatial, we have a few different subcategories of that as well. So vector data is probably the prominent or most predominant type of spatial data within a GIS. And really what we're talking about here is points, lines, and polygons. So if that sounds familiar to you from your time in geometry class, you are right. We are talking about basically a Cartesian coordinate system with an x-axis and a y-axis, and you can define the location of things by what values they correspond to on the x and y-axis. And really that's what mapping is all about, right? So in this example, it's a nice example because it shows you how points, lines, and polygons might come together in a map that you might use one day. This is probably a subdivision or a residential area. I'm imagining that the lines here are pipelines, and the points that are represented there might be pipe fittings. And then the polygons, the shaded areas, would be the parcels, the land ownership parcels. So that gives you an idea of what vector data looks like and what it consists of. The other type of spatial data is raster data, and we're all pretty much familiar with this concept because we talk about screens and monitors and what the resolution is and how many pixels there are and things like that. And raster is an array of cells. Each cell is the same size, and each cell is assigned a value. And raster data is pretty much used for imagery, of course, and also things like elevation or remotely sensed data. It might be wind speed and velocity and direction. It could be the presence of a certain chemical in the air or something like that. So raster data is used mostly in the natural sciences, whereas vector data is used in everything, you know, anything that you can think of pretty much. And I want to throw in a mention here. There's also what's known as mesh. It's kind of new, at least to me. I know very little about it, except I know that it exists. But with mesh data, it's focusing on an unstructured grid. So you could have triangles, or you could have all kinds of shapes, right? And you have vertices where the shapes come together. Edges are on the edges of these shapes, and the faces are the shapes themselves. And it could be used to represent either two-dimensional or three-dimensional surfaces. And yeah, I have seen mesh referred to in terms of elevation models, and I think some other things too. It's really more of a cutting edge almost kind of thing. It's been around for a while, but people are doing more and more with mesh data these days. But really raster and vector are the two predominant types of spatial data. So let's take a quick look at how vector compares to raster in terms of their basic components. For vector, it's very good at topology, which means the relationship, the spatial relationship between one feature on the map and another. This one is next to this one is intersected by that one, that kind of thing. So it makes it good for things like network analysis and many other types of operations you might want to impose on the map. Vector model is a complex data structure, for sure. But it ends up giving you a map that looks more like the maps that people might have drawn by hand in the past. Whereas a raster model, the advantage of that is that it can represent high spatial variability. So especially if you're thinking of remotely sensed data, it's going to pick up grid by grid. What's the value? What's the value? What's the value? It can show that variability. It's very simple structure compared to the vector model. But as we saw on that illustration, the maps look kind of blocky. So not your first choice if you want smooth looking lines and things like that. Of course, a lot depends on the grid cell size too. The finer the grid, the better it looks. So for tabular data, that's the other type. We had spatial data, now we're talking about tabular data. And the big deal with tabular data is when you have vector data, you've got what's called an attribute table that's often hidden in a GIS, but it's there and it's very powerful because the attribute table is the thing that stores the characteristics of the map features. So on this illustration, you can see that after you have your row of headers, all the other rows going down correspond to a particular feature on the map. And then all the columns give a type of information regarding the features on the map. And you can see it's not just numerical. You can have text, you can have alphanumeric, you can have hyperlinks. Lots of things can go in those cells. But this is what makes a GIS so powerful because you can, recombine the information in all kinds of ways. You can sort out just the features that have a particular type of attribute, all that kind of thing. And the table has an ID number in one of the columns, and the spatial data file also has an ID number that's stored with it. And that ID number is what links the table to the spatial feature. Okay, does that make sense? I hope so. So that's how that goes. Now let's talk about some data sources, meaning where could you go look for data for a GIS? Well, first we'll talk about spatial data. So here I'm thinking of you definitely need the shapes, the outlines of the either polygons or the lines. How is that going to come about? Well, if you're the one creating the data, you're going to be the one drafting the points, the lines, or the polygons. If you have access to, say, a drone or something, and you put a sensor or a camera on it, then you might be acquiring raster data that way. But for most of us, we're probably going to go out looking for existing files of spatial data. It could be vector or raster. And the types of places you might want to look are called data repositories. And if they're just for geospatial information, they're probably known as geospatial data repositories. Or you might look for a data portal. And if it's just relating to spatial data, it's probably called a geoportal. And so what kind of places have these repositories and portals? Government agencies, everything from your local city all the way up to the national level, they provide lots of data for use. The United Nations and World Bank are more on a global level. They've got tons of data. Nonprofits often have some data that they share out in GIS form. Universities often host repositories or portals. And then if you are using Esri products, Esri is the company that produces ArcGIS software, which is the predominant GIS being used out there today. If you are using ArcGIS, you have access to Living Atlas of the World, which is something that Esri has compiled. And that has thousands of data layers on all types of topics. And the nice thing about it is you can just pull it in from your ArcGIS session and use it right there. And it's been vetted a little bit or a lot, so it should be pretty reliable data there. And lastly, your coworkers or collaborators might supply you with some spatial data as well. And I wanted to mention at the bottom here that sometimes you can find vector files that only contain the shapes and the basic ID. And so it's kind of like a shell on which you can populate it with data that you have from some other source. But a lot of times in these repositories and portals, you get both the spatial data and some attributes that that entity has added to it as well. So there's kind of two types of spatial data there. One is just giving the spatial files, one is giving you some attribute data. So where are you going to get tabular data? Maybe you have this nice shell of, say, the United States, and you've got some data for the United States, and how do you get that in there? Or where are you going to find that tabular data? Well, again, if you're the one doing the mapping, you will be supplying the data for the attribute table. If you have a field apps or taking surveys or something like that, you'll get the data from there. But again, there's lots of existing sources for data that you could go look for. And it might be in tabular format, it might be from a database or a GPS file. But whenever you find tabular data and you want to use it in a GIS, it's got to have one column in there that has geospatial information that your spatial file will recognize or your GIS will recognize. And if it doesn't, you're not totally sunk, but you just might need to add a column that has that kind of data in it. What's an example of this? Well, maybe you have the state of California and you've got the counties in California, and you've got data that's by census tract, say. The GIS is not going to recognize data that is conglomerated by census tract unless it's got a spatial file that has the census tract boundaries in it, that kind of thing. So you need to make it match pretty much. So that's just something to think about as you're out there gathering up attribute or tabular data. So some pointers about your tabular file. When you're bringing in a CSV or a Google Sheet into a GIS, again, each column is going to represent a different type of information. And it's got to have that spatial data column, at least one. And if you find data that has latitude and longitude, I believe for most GISs, those need to be in separate columns. So if it comes to you in one column, like latitude, comma, longitude, all in one cell, you're going to have to do a little bit of work to get those into two separate columns. Place names, addresses, whatever it is, you need a column, at least one column in your table that has that kind of information. Each column has a header. And here's some tips about those headers. Don't use special characters in them, including lead or ending spaces. That has driven me crazy in the past. I wasn't aware that I had an ending space at the end of my header, and it was causing all kinds of problems. And also make sure each header is unique. If you have two headers that are accidentally exactly the same, that's going to give the system fits. So don't do that. And be sure you use consistent formatting in a given column. So for instance, if you have a team that's gathering data and it's a percentage of something and different people are populating different parts of that column, if one person's using 0.62, 0.44, and another person is using 44%, 62%, that's not going to work too well. So just make sure your formatting is all consistent for that column. So that's about the columns. Now the rows, as you remember, are each supposed to represent a different feature on the map. So we don't want any blank rows, and we don't want to use any subheaders in the table that we're trying to upload to a GIS. And I'll give you an example of that. This was from a project I helped a few students with last year. And on the left is what they came in with. It's a perfectly fine way of organizing data. They have the counties of California, starting with Alameda, and they had some data by county, by certain years were in their columns. But you can see the problem. They have multiple rows for one county. And then they have line 2, it has some subheaders in there. That's no good. So what we had to do was get the students to kind of reformat their table or create a new table that looked more like what you see on the bottom, where there's just one row for Alameda County and all these columns that can keep going and going and going with all the data just for that county. And then the next row down will be for the next county and so forth and so on. So that you might have some work there to do to get the table in the right format for the GIS to accept. So let's talk about some file formats that are out there. And first, let's talk about the file types associated with vector data. The big one here is shapefiles. They are read by nearly all GIS systems. They include geometry and attributes, and also projection information, which we will talk about in just a little bit. And it's kind of confusing. Well, it's confusing in a few different ways. And one way is that a shapefile is actually a set of files. It's not a singular file. It's going to consist of at least 3 and often more files than that, and you will need all of them. So one mistake I have made a time or two was opening a folder that had a shapefile in it, or I was told this is your shapefile, and I opened up the folder and there's all these different files with all these different file extensions, and I'm like, well, I only need the shapefile, and this one is SHP, and that's the shapefile, so I'll just pull this one out. That doesn't work. You're going to need to load in all of the files that come in your shapefile folder into the GIS. And you can see that this is just one example, and you can see all the different file extensions here. This was a graphic I found elsewhere, and there's a lot of possibilities there. So not everything that's over here is over here, and vice versa. There are some in this particular shapefile that aren't even on this list. So there's a whole bunch of possibilities is the basic point. So shapefiles are confusing in a couple different ways, including the fact that one of them is actually has the suffix SHP for shapefile. Yeah. So let's talk about some other vector data file formats. Another popular one that you may have heard of are KMLs or KMZs. These are associated with Google Earth. So they contain geometry and attributes, and also configuration options that are specific to Google Earth. It is possible to transform or repurpose a KML or KMZ into a shapefile and vice versa. Interoperability is fairly common in this world, but just so you know that that's a possibility, but you're going to have to do a little bit of work before you can say pop one into a ArcGIS session or something like that. File geodatabase, I was a little surprised to see this is consistently included in vector data file formats when I was researching this workshop, because it can contain rasters and it can contain other things, but often it does contain vector data. And it's used in Esri software, but it's not supported in open source GIS platforms. So you would not be able to open a geodatabase in QGIS, for instance. I've included a link. You can see that Data Curation Network has put together a geodatabase primer full of information. So I wanted to include that link there for you. You can learn much more about it. But it's one of the basic things that will come up, especially if you're using ArcGIS software. A geo package, on the other hand, is kind of similar, but this is what's used in open format GIS, such as QGIS. And it's built on top of SQLite. And then GeoJSON is another one where Data Curation Network has produced a primer on it. And this is used for web apps, web maps mostly. So you'll see it as an API output a lot. Then we have, moving on to raster data. So a really nice one is GeoTIFF, and it's going to have that same file extension as just a regular TIFF. But if it's identified as a GeoTIFF, that's great, because what this means is that you can bring it into your GIS session, and it will plop down right where it's supposed to be. If it's a regular TIFF, if it doesn't have this georeferencing information in it, you could bring it into your session and the GIS has no idea where to put it. Even if it's something like super obvious, like a map of Italy, where it's like, yes, my 4-year-old could match this up, but the GIS is going to know what to do with it unless it has that georeferencing information in it. So if you have a choice between a TIFF and a GeoTIFF, go with the GeoTIFF, because that'll load right in and save you some work. Mr. SID is another type of raster file that also has georeferencing in it. And this is what the US Geological Survey uses for most of their scanned products. Then, like I said, there's TIFFs, there's just regular TIFFs and other image formats that you can load in. I think TIFF, though, is the preferred one that works the best with GIS. And then there's Imagine, which here we're getting into things I don't know a whole lot about, but this would be for single band or multi-band data. And it says sometimes accompanied by an XML file containing metadata. I would hope it would always be associated with metadata, and we'll talk about metadata in just a second here. And then you can see a couple other options down there at the bottom of the screen. There's just a whole bunch of data formats for remotely sensed data, too numerous to list, as they say. But that just gives you a feel of vector versus raster and some of the basic file formats you might encounter. So let's talk about data properties. And we're going to start talking about data properties by talking about metadata. For those of you who are not familiar with metadata, it's a file of information that captures the basic characteristics of the resource. Very handy when you are searching the internet for data. If there's metadata to read, you will want to read it because it will tell you a lot about what you're thinking about downloading before you actually get it into your system. Who created the data and who published the data? Those could be two different things. I have been involved in projects where it definitely was two different entities there. And also the contact information if you wanted to ask questions about the data. Metadata will talk about what information is contained in this resource, especially like a data dictionary that runs you through all the possibilities for all the information in each column kind of thing is pretty much what a data dictionary does. When the data was collected and when it was published, again, these can be two different things. I've been burned a time or two when I found published data that was pretty recent and I'm like, yay, this is exactly what I need. And then I find out that although it was published last year, the data was collected 6 years ago. And then it's like, oh no, this is not what I need. And so that can happen to you as well, I'm sure. And if the agency producing the data plans to update it, the metadata will tell you what they expect their update frequency to be, or at least if it's good metadata, that will be included. Where the data is, so what location is covered. And this is often expressed by a bounding box. And in particular, I always forget which two coordinates it is, but they might give you the coordinate of the lower left and the upper right box, and then you can create the rectangle from there. But anything within that box, or let me put it that way, the data will be inside that box. It might not cover the entire box, but at least everything will be somewhere within that box, and none of the data will be outside those coordinates that they give you for the bounding box. And also good metadata will talk to you about if there's any known gaps in the coverage, the spatial coverage within the bounding box. So sometimes it could be something like it's the continental United States except military bases are excluded or something like that. That would be good information to have. Why would be the goals that they had for creating the resource. That's often very helpful to understand what you might and might not encounter. And how the data was collected. Was it from photo interpretation? Was it from people out in the field? Was it from other data sources? That kind of thing. And if they can also talk about what errors might be in the data, that's also very helpful. So in addition to all those journalistic questions, metadata can also talk about scale, like what scale they were using when they collected the data. Were they zoomed way in or were they zoomed way out? Because that will affect the quality of the data for your purposes. The projection and coordinate system, which we are going to talk about in just a little bit here. And the licensing or the usage restrictions. So they will tell you about if you're going to use this data, please attribute it to this source in this format and that kind of thing, or whatever their restrictions are on the use of the data should be in the metadata. So you can see how important it is. And it's a kind of a tedious task to put it together. A lot of people don't like to do metadata, but if you are creating geospatial data that you plan to share, especially if you plan to share it out, please do take the time to provide the metadata for it, because it will help a lot of people down the line who might be interested in using it. Okay, so projections. This is going to be a real quick overview of projections and coordinate systems and why you need to be concerned with them. Projections are the way that mappers over the centuries have figured out to get what's on the curved surface of our Earth onto a flat two-dimensional canvas, whether it's paper or nowadays it's our computer screens, right? If you do a mental exercise trying to picture how would you do this, it's not that easy. You just can't peel a layer off the top of the globe and smash it down and it's all going to work out well. Yeah, it's just, there's a lot of things that can go wrong that way. So smart people over the years have figured out different ways of doing the best they can to capture what's on the surface of the Earth. You can see 3 of them here. And I think you've probably seen maps that have these different projections. And for instance, with the one on top, the Mercator projection or cylindrical projection, those maps are the ones where Greenland is really, really big, right? But maybe with some of these other projections, the size of Greenland is not especially distorted, kind of thing. So the thing is that different projections succeed in different areas, but in any projection, something has to be distorted, whether it's the shape or the area or the distance or the direction or some combination of those things. So, you know, projections are chosen based on what your needs are. So for instance, mariners are really fond of projections where distance and direction are preserved. They're not so concerned about the shape and the area of things. They just want to know which direction do I go and how far is it, kind of thing, right? But you know, the opposite too, there are some projections that preserve shape and area pretty well, but you would not want to use it for navigation. So none of them are wrong, but when you bring them all together in this old but good illustration, you can see that you have some problems, especially the further you get away from where they all fit together in Kansas there. Got big problems in Florida and in Maine and in Washington State, so forth. So not all data that you're going to find will be in the same projection. So you might be saying to yourself, oh no, what if I find like perfect data and it's just not in the same projection? Am I sunk? Is this like a non-starter? And the answer is no, and we're going to talk about what to do about that in just a second. But I also, before we get there, I need to talk about coordinate systems and datum. So coordinate systems, there are hundreds of them. There are a few that are global or spherical, and these are the ones we are familiar with, is latitude and longitude. So we're talking about angles, right? 45 degrees north, 110 degrees west, all that kind of good stuff. But once the Earth's surface has been projected onto a flat surface, then we can talk about something we're a little more comfortable with in terms of our Cartesian coordinates and an X value and a Y value. We can talk about things like UTM coordinates is one popular one, state plane is another one. There's a whole bunch, and there's a lot of subsets of each of those. There's just hundreds of them. And then on top of having all these different coordinate systems and different projections, we've got something called datum, which is what ties a projection to the imperfect surface of the Earth. And there are a few standard datums, and they change over time. There's another one coming up in 2022, I think, that's going to replace NAD 83. So yeah, be on the lookout for that, right? But what's the big deal about datum? Well, this little quote here says that even if you've got something in the same projection, if the datum used to produce the map was different from one to the other, then the coordinates aren't going to match up. So that's just like, there's 3 things here now that you've got to kind of worry about when you're bringing in data from different sources that have different projections and coordinate systems and datum. Well, there's good news and mostly good news. Many GIS will reproject data on the fly. So if you have loaded in one set of data and it's in one particular coordinate system, and then you load in a second one that's a different coordinate system, it'll crank through and it will make it match each time. So that's kind of okay. You won't notice the offset when it does this. What's okay for viewing. However, data is slower to draw because the GIS has to think really hard every time you move around, like, oh, I I have to reproject this again. Not so okay for analysis. It's really going to mess up things if you just let it reproject on the fly. So the solution is that there are tools in the GIS that will enable you to project the new data once and for all into the same coordinate system as your other layers. So you just go through the process of using those tools, and then it's settled, and you can go on without any worries about anything mismatching or being in the wrong place. Now let's talk about data quality. So here are some considerations if you're looking for data out there, and also if you are in a project where you are creating data. You have to think about what scale range was used, or what you are going to use in the mapping. Are you going to zoom way in to make all these delineations, or are you going to be zoomed pretty far out? Or were the creators of the data zoomed in or out? How detailed are the delineations? How accurate as well? So you can have something that's really detailed, and every little nuance of every little line is very, particular. But if it's all offset, or they didn't match it up very well, that's not a good thing, right? And then a consideration under this, where I used to work, we called it minimum mapping resolution. So this was something that we negotiated with our clients, or that we established with our clients, saying that if we're mapping, say, vegetation, anything that's in this, well, I'll just pick an example, 2.5 acres, right? So if it's something that's smaller than 2.5 acres and it's distinct, we're not going to be able to map that. It's just not feasible in our budget and our time allocation, but we will map anything that's 2.5 acres or greater. So that's something to look at when you're looking at data, or to decide at the start of your project, is how tiny are we going to go without breaking the budget, or ruining our timeline or anything like that. How accurate are the point locations? So we were talking about the accuracy of line and polygon delineations in the previous bullet. Now this is just for points. You don't have to draw anything, but you can still have points that are, offset unintentionally, and that's not a good thing too. So you might want to take a look at that. Is the coverage complete? Like I mentioned, there might be gaps, like the military installations were left out, or tribal lands, or something like that. And then sometimes you might have data coming from different sources, or even from the same source, where they have overlaps of data. And hopefully they all overlap perfectly, but you never know. That doesn't always happen. If there are adjoining tiles, do they match up perfectly? And I'm talking about both the spatial delineations and maybe the attributes that are assigned to the things on adjoining tiles may be different. I did experience this early in my career. I was using a soil survey where it was published and should have been fine, but 2 adjoining sheets, just in one little area, the polygons did not correspond. They did not line up at the edge. The codes, or the attributes that were assigned to the polygons, were different. I had to contact the Soil Conservation Service and say, this is what I'm seeing. And they said, that's impossible. These maps have been gone through quality control twice or 3 times before they were published. So I actually had to go down there and show them like, I've got this doesn't match up. And they're like, oh, you're right, they don't. So even with something that's been produced by the government and has gone through rigorous quality control, there could still be some issues like that. And then you have to decide how you would reconcile the differences if that's something that's really important in your project. For data considerations, so now we're thinking more about the attributes. How granular is that data? So to give a land use example, somebody could say, I have mapped land use for the entire county of Riverside. Well, they might have used a classification where they broke it into residential, or commercial, or industrial, or agricultural, that kind of thing. Or it could have been something which much more finer detail, like single family residential low density, single family residential high density, multifamily residential low density, that kind of thing. For commercial, instead of just saying it's all commercial, well, it could be broken into something like regional shopping center versus a sports venue versus something else, So Just because it says it's land use or vegetation or poverty levels or something, it doesn't necessarily mean it's what you're thinking it means as far as level of detail on what you're going to get with the data. Does the data contain a significant proportion of null values? So thinking about that attribute table and a column in that attribute table, it is possible that published data might not be 100% full in that column that you are most interested in. And I found this as well a couple of times, and it really kind of threw me for a loop because I was really hoping for like complete data, and for whatever reason, there were just so many features that did not have any data for it. It was almost like I can't use this. If you have adjoining sources with different data structures, how we resolve the differences. So that's more, again, going up to that first point where if you have something that's very general in the way they've classified the information versus something that's more detailed, and they come together, how are you going to do that where they match together? Does the timeliness of the data meet your needs? And sometimes there's trade-offs among all these. Like, again, I had this experience. I was tasked to hunt for data for the continent of Africa, and I might find something from 15 years ago that was pretty complete data for the whole continent, or I might find something from 3 years ago that was, of course, more timely, and that's what we wanted, but only maybe 8 or 9 of all the African countries had any data there at all. So you have to make those trade-offs on what's going to serve my purposes better, because I can't have exactly what I want. So where do I go, and which data source do I try to use? Also consider if the source is authoritative. All kinds of people are putting all kinds of stuff out there. You would want to try to make sure that you find something that is authoritative. And even with authoritative sources, everybody comes at things with their own biases or filters, whether it's intentional or not. And so you might want to consider what biases or filters may have been applied in mapping, and how that might have affected what you're going to be seeing on your map. And here are some tips for if you're going to be doing mapping. Some pretty quick tips that you can follow or think about at the beginning before you get going too far. So put some thought into how you're going to structure your data. If what you're mapping lends itself to a hierarchical classification, that is great. And rule of thumb is if you can go as fine as, or pick a level that you can go fine, like that land use example I gave on the other slide. The more granular you can get there, the easier it is to create both a really detailed map or something at a higher level. But if you've only captured the data at that high level, it's going to be real hard to break it down later. A lot more work and effort. So capture as much information as you can at the first pass, rather than thinking, oh, maybe I'd have to go back and do it all again and break it down into finer categories later. That's like not a good way to go. If you have a hierarchical classification in particular, an option is to consider is using codes, like numerical codes, instead of very long character strings. So for instance, again, with that land use example, maybe we would make the codes 4 digits long, and 1000 would be residential, and maybe 1100 would be single family residential, and 1200 would be multi-family residential. And maybe the third digit would be whether it's low density or high density. So if you can set it up that way, you get a lot of possibilities for data analysis later in a hierarchical classification. It's possible for you to establish valid values, or what are called attribute domains, and do that when you can. So maybe you have one column of data where there's only going to be 6 or 8 possible answers, and nothing else. Nobody else has to populate anything else in there. So you can set that up. So if somebody tries to type in, a 42 when they were supposed to be typing in, like 0% or something, something that's totally different, they're not going to be able to do that. So that'll cut down on the number of errors that will go through. You can also establish consistency rules that can be run at the end of your mapping. So for instance, if you have a land cover that's showing up as a lake, you don't want it to have a slope greater than 0. Lakes don't work that way, so you can just guard against those kind of spatial errors as well. You can use snapping, and what this is, if you want certain features to be absolutely coincidental in space, you can use snapping tools to make that happen. One example would be maybe you have the, like way back, we saw that example of pipe fittings and where the pipes came together. If you're creating a point where those pipes come together, you don't want it to be offset at all. You want it to be right on that intersection. So snapping will allow you to do that. There's something else that's called topology checks that you would want to take care of. And this is especially important with lines or polygons. And what this will do is, if you are supposed to have a polygon coverage that's seamless, there would be no overlaps. You wouldn't expect polygons to overlap, and you wouldn't want any gaps between them. Topology is the kind of thing that it will check and make sure that you don't have them. And if you do have them, it'll show you where they are and give you the opportunity to fix them. So those are some ways that you can assure data quality as you're mapping on your project. Okay, here's the last little topic that we're going to cover, data management. And I believe my co-host today, Riley, is going to put a link in the chat for an assessment. So we're getting close to the end of the workshop. And if you can at some point follow that link and just let us know how this went for you, that would be greatly appreciated. That will help us figure it out for later, what to do better next time, all that kind of stuff. So anyway, thanks for that. Data management. So some of this will be familiar to you data science people. You have heard a lot of this before, I'm sure. 3-2-1 rule for storing data. Always a good idea to have 3 copies of your data, 2 different types of media, 1 copy is offsite. You can create a master project folder, and if you're gathering data from a bunch of sources, have 1 folder for each data set, and there's the naming convention that's recommended. Have an archive folder to keep the unaltered copies of your source data files. Very important if you're going to start manipulating data. And if something goes wonky, you want to be able to get back to where you started without having to try to reproduce that. So yes, always keep a clean copy that you haven't messed with somewhere where you can get back to it if you need to. If you're working with sensitive data or there are privacy concerns with the data that you have, please do consider making some file access restrictions. And it's possible in a GIS to mask point data locations, obscure them. There's a few different ways that can happen. If you don't want people to know exactly the exact location of something out of privacy reasons. And lastly, this is from a webinar I watched almost a year ago now, and it was called Data Management for GIS Projects. And I've included the link there. It's been recorded, so you can go back and watch it as well. So these are just a few of the tips that you would find in this webinar if data management is of interest to you. Create a GIS project plan and a data management plan at the outset of your project. Very important. I have tried to go down this route of kind of creating a project without these kind of plans at the outset, and it's not been a good thing. So yeah, it's kind of tedious at the beginning and you don't really know what you're getting into, but do try to get a structure. Think about some of those considerations I shared on earlier slides right at the outset. It'll go much better. Yeah. You can have 1 team member be the data sheriff. So 1 team member would be responsible for making sure people follow the established rules for file naming and folder naming and metadata and all that good stuff. So yeah, that's a good idea for your project. Make file labeling clear, concise, and consistent. Create folders for each iterations of your process data. In addition to having that pure, clean archived copy of what you started with, you're going to create folders for each step of the way, hopefully, and including a text file explaining what you did there. And then when you're looking for where this data is going to be stored when you're all done, in this webinar, they suggested your institution, if they have a portal or a repository, rather, go ahead and put it there. Or if not, or if it makes more sense to find a subject-specific data repository, go ahead and use that one. Okay, that is the end of my presentation. It came out pretty well time-wise, so we do have some time. I'm going to share with you my contact information there real quick. I'd be happy to follow up with you on any questions you might have. And let me stop sharing my screen, and we can take a look at any questions that came in the chat. Well, the completeness of the data, somebody asked in a direct message about the completeness of the data be specified in the metadata. So it should be, you know how I said people get kind of cranky about creating metadata? So sometimes people don't fill it in completely, sad to say. So if they've done a good job, they will talk about the completeness, but no guarantees there. I think maybe it's getting harder and harder to leave things blank, but yeah, honestly, people cut corners, you know how it is, so yeah. Can I recommend tools that assist with metadata collection? So this is something I in particular have not dealt with a whole lot myself. I know that within ArcGIS, there are tools that will help you create the metadata. They'll actually extract some things from what has been mapped, and then you would just need to fill in some things it couldn't have guessed. You know, it doesn't know about what the team members' names are and things like that. But that is something that can be built. I believe in QGIS, it's not as robust. I'm trying to remember. I think QGIS has a lot of what's called plugins, and I think there are some that help with metadata. I could be wrong on this, but yeah, I would have to look up some more metadata tools that might be available out there. I know it's a really big concern these days, especially with so much data being available online, and people who are running geoportals or geospatial data repositories have a lot of concern about inconsistent metadata, because they're trying to serve up complete information to the users. And yeah, so that is a very, very good topic, an important one too. Okay, were there any other questions? So it's a big topic, and I only skimmed the surface barely, and there's other things we could have talked about today, but I hope this will give you some help as you go along in learning more about GIS, or maybe you already know some things about GIS, but this presented a few more things that you weren't really aware of or weren't super focused on. So hopefully this helped in some way at some point. I will keep the call going for a while, but I see it's 5 till. So for those of you who have to leave, thanks for joining us today. I hope that you have a good rest of your day and that your exploration of GIS continues. And I will stop the recording now, but please do stay on the line if you need to, if you'd like to ask me any more questions or have any conversation around some of the topics we brought up. Thank you.